Introducing the sample database. The Book Biz Database is not a real-world database, but simply a learning tool. Its purpose is to provide you with a small collection of interesting data to manipulate as you study SQL syntax and semantics. The Book Biz Database is about a fictitious publishing company that has 3 subsidiary publishing lines. The database stores information that editors, administrators, executives might want about books, their authors, their editors, and the company's financial arrangements. This database can produce many kinds of reports summarizing current sales, comparing different book lines, discovering which editors work with which authors, and so on. In real life, the database would probably support many other uses and many more reports. Users of the Book Biz database can pose many different questions, including these: which authors live in California? Which business books cost more than $19.95? Who has written the greatest number of books? How much do we owe the author of Life Without Fear? What's the average advance paid for all the psychology books? How would increasing the prices of all the cookbooks by 10% affect royalty payments? How are sales of the computer subsidiary doing? Which books are most popular? As a database designer, don't try to just imagine which questions are most important to the future users of the database you're designing. You need to research users' needs by reviewing current data collection and retrieval methods, and by interviewing your users individually, in groups, or both. One important area of investigation is the organization's business rules and policies that affect the data. The policies of the publisher for which BookBiz is being designed include these. An author may have written more than one book. A book may have been a collaborative project of more than one author. The order of the authors' names on the title page is crucial information, as is the percentage of the royalties each will collect. An editor may be working on more than one book, and a single book may be assigned more than one editor. A sales order may be for one or more titles. Data, entities, and relationships. We begin designing BookBiz using a somewhat simplified version of entity relationship modeling. At the most basic level, entity relationship modeling means identifying the things, entities, about which information will be stored in the database system, the properties of these entities, the relationships among the entities. Entities, things with an independent existence. Let's start by considering some of the BookBiz database entities. If we ignore for the moment most of the financial information that BookBiz tracks, a preliminary list of entities might look like this: the authors who have written books published by the company, the books themselves, the editors working for the company, the subsidiary publishing houses owned by the company. Each item in this list is an entity with an independent existence in the world under consideration, that is, the world of the BookBiz database. Each is represented in the database by a table. The entities have certain properties that are to be recorded in the database. Among the properties are book's name, book's price, book's publication date, author's name, author's address, author's telephone number, editor's name, editor's address, editor's phone number, publisher's name, publisher's address. Each property or attribute of the entity in question, the author, book, editor, or publishing subsidiary, is a potential column in the database. Column names should be selected for clarity to describe the kinds of values the column holds, and brevity to minimize both typing and the width of displays. The list of entities and properties we've identified can be seen as a first tentative step in deciding on the tables and columns to be included in the database. You might sketch these decisions like this. Diagramming entities and attributes. Another way to view the information is in an entity relationship diagram, as shown in Figure 2.1. The usual convention is to display each table as a box with columns listed inside. This sketch of 4 tables, each with several columns, is a first stab at the structure of the database. You can imagine that the tables will contain multiple rows of data. Each row in a table represents an occurrence or instance of the entity, that is, a single book, author, editor, or publishing company. Primary keys. One of the jobs of the database design is to provide a way to distinguish among entity occurrences so that the system can retrieve a particular row. As you might have guessed, rows representing occurrences of entities are distinguished from each other by the values of the table's primary key. In fact, as we've said, the informal definition of a primary key is the column or combination of columns that uniquely identifies the row. What is the primary key for each of these tables? Consider the authors table. Of the columns identified so far, name is the obvious candidate for the primary key. An author's name distinguishes him or her from other authors, but the name column is problematic as a primary key for several reasons. First, the value in name is made up of the author's first name and last name. Combining first and last names in one column is a bad idea, if only because it would be difficult or impossible to sort authors alphabetically by last name. So the first necessary change is to split the name column in both authors and editors into 2 columns. See Figure 2.2. Now, with regard to the question of identifying the primary key of the author's table, it might seem as though the combination of the columns AU_L name and AU_F name is the right choice. In fact, that combination would work pretty well until the table grew large enough to contain duplicate names. Once there are 2 or more of the same name, the AU_L name and AU_F name combination would no longer uniquely identify each author. Another problem with using values like names as unique identifiers is the frequency with which they are entered incorrectly. It's easy to misspell names. Other kinds of proper names, like names of companies or organizations, are even worse. To a computer, these differently spelled names are all different companies. Finally, consider volatility. Personal names are likely to change due to marriage or divorce. Company names may succumb to rebranding or acquisition. For these reasons, it's usually a good idea to create a separate column explicitly designed to serve as the primary key. Real-world examples of such unique identifiers are common. Social security numbers, employee identification numbers, license plate numbers, purchase order numbers, student identification numbers, airline flight numbers, and so on. In the authors and editors tables, we'll use social security numbers. For the titles and publishers tables, we'll arbitrarily assign some identifying codes. As a record-keeping convention, we'll underline these columns to show they are primary keys. See Figure 2.3. One-to-many relationships. At this point, we have structures for 4 tables in the book Biz Database: authors, titles, editors, and publishers. Some of the properties of each of the entities described by the tables have been specified, and a primary key has been identified for each table. However, you may have noticed that certain important relationships among the data are not yet represented in the proposed design. For example, there's nothing in these 4 tables that tells you about the connection between a particular publisher and the books it puts out. The relationship between publishers and books can be described as one-to-many. Each book has only one publisher, while each publisher can produce many books. One-to-many relationships among data are often written as 1 to n or 1:n. Representing the relationship. How can you represent this one-to-many relationship? In the book Biz Database, a first impulse might be to add a column for title_ID in the publisher's table, as shown in figure 2.4. The title_ID column in the publisher's table is a foreign key. You can use it to point to specific rows in the titles table and join title and publisher information. Unfortunately, this proposed solution sends your database design off in the wrong direction. Remember, the data relationship we're modeling, one publisher, many books, and consider what happens whenever a new book is published. You'll add a new row to titles with book name, price, and so on. For each row in titles, you'll have to add a row to publishers. The publishers row will repeat 3 columns of existing information: publisher number, name, and address, and add 1 column of new information, title_ID, to refer to the more in-depth description in the titles table. Recall that one of the goals of database design is to control redundancy, because redundancy introduces opportunities for error. A better solution is to add a publisher's foreign key to the titles table. See figure 2.5. When a new book comes out, add a row with a pub_ID column to the titles table. You don't need to do anything to the publishers table unless the company takes on a new subsidiary. With these changes, a structure begins to emerge. The publishers table has 1 row for each publisher. The titles table has 1 row for each book. Publisher ID numbers are repeated in the titles table because there are many books for each publisher, but that's still less redundancy than would occur by choosing other design options. You can use the logical connection between the pub_ID columns in titles and publishers for joining the 2 tables. In other words, this design is planned with the join operation in mind to allow users to retrieve information about publishers and titles in one query. In the publishers table, pub_ID is the primary key. In the titles table, the pub_ID column is a foreign key. The relational model requires that one-to-many relationships be represented by means of primary key, foreign key pairings. Foreign keys. Like the concept of primary key, the concept of foreign key is crucial in database design. A foreign key is a column or combination of columns in one table, the values of which match those of the primary key in some other table. A consideration of the logical relationship between the information in the primary and foreign key columns introduces some further questions. What happens in the pub_id column of the titles table if the row describing the publisher is deleted from or changed in the publisher's table? Should the description of a book be allowed to refer to a publisher ID number if that publisher no longer exists in the database? It doesn't make sense logically, and it violates the definition of a foreign key, which requires the value in a foreign key column to match the value in a primary key column somewhere in the database. However, this is not an unusual situation in real life. How you handle it depends on your business rules. A complete database design should include planning for primary key, foreign key consistency, or referential integrity. For example, when a publisher's ID number is updated in or deleted from the publisher's table, the system should automatically reproduce the change in the titles table, either by updating all corresponding values in the titles table pub_id column, or by cascading, propagating the deletions in publishers to titles rows with matching pub_ids. When a new title is added, the system should have a way of verifying that the associated pub_id is valid, that is, that it exists in the publisher's table. At this point, just make a note of these issues. The next chapter gives hints on how to handle some primary key, foreign key issues with the references constraints in the create table statement. Vendors also have introduced implementation-specific ways to control integrity, such as SQL extensions for procedural code that can be executed in the database, often called procedures or triggers, discussed in Chapter 10. Many-to-many relationships. After identifying all the one-to-many relationships in the book Biz Database and associating them with primary key, foreign key pairings, the next step is to consider other kinds of data relationships. For example, how are authors and books related? Some books are written by more than one author, and some authors have written more than one book. In other words, authors and books have a many-to-many relationship, often written as N-to-N or N:(N), and sometimes called an association. According to entity relationship theory, associations in relational databases should be represented as tables of their own. In other words, the book Biz Database needs a table for authors, a table for titles, and a table to represent the association between them, as shown in Figure 2.6. The title authors table represents the many-to-many relationship between authors and books. It is a base table just like titles and authors, but it is an association rather than an independent entity. When a user of the book Biz Database wants information about who wrote which books, he or she writes a join query that uses the title authors table as a connecting table between titles and authors. The title authors and titles tables join on their respective title_id columns. Title authors and authors join on each table's AU_ID column. In other words, title_ID in title authors is a foreign key whose matching primary key is title_ID in titles. AU_ID in title authors is the foreign key whose matching primary key is AU_ID in authors. What is the primary key in title authors? Neither the author ID nor the title ID uniquely identifies rows in title authors. The IDs of titles with more than one author are repeated, as are the IDs of authors who have written more than one book. However, each title ID, author ID combination is unique. The primary key of title authors, then, is the combination of title underscore ID and AU underscore ID. The editors and titles tables have a similar relationship. An editor can work on more than one book, and a book can have multiple editors. This many-to-many relationship also calls for a connecting table. One-to-one relationships. Take a final look at the entities. If you find a one-to-one relationship between two tables, you might be better off collapsing them into one table. However, maintaining a one-to-one relationship could improve response speed in queries. For example, if you have information about titles that you seldom use, notes on copyright information, lists of change pages, for example, you might want to keep it in a separate table so that you don't have to access the information when running common queries. Generally speaking, you should avoid one-to-one structures when you first design a database, unless you know your data very well. The entity relationship approach summarized. Here is a review list of the basic steps discussed so far. Represent each independent entity, book, author, publisher, editor, employees, department, student, course, company, and so on, as a base table. Represent each property of an entity, author's address, book's price, and so on, as a column of the entities table. Make sure each table has a primary key. The key may be an existing property, a name, or an artificial one that you add, a social security number, an order number, or a combination of two or more properties. At any rate, it must uniquely describe each row. Locate one-to-many relationships between tables. Check that there is a foreign key column in the many table pointing to the primary key column in the one table. Consider the referential integrity constraints associated with each foreign key. Represent each many-to-many relationship or association as a connecting table between the two tables that participate in the association. Include in this connecting table foreign keys that point to the entity tables. The primary key of the connecting table is often the combination of those foreign keys. Collapse one-to-one relationships into a single table where appropriate. After each pass, look at your needs again. Have you incorporated the business rules? Can you get the information you need? Such a check against the BookBiz requirements reveals a few shortcomings. There's no way to record author order or royalty split. There's also no notation for contracts, and you need to keep track of advances. Sales are another topic not covered in this design. With these points in mind, you might modify the ER diagram as in Figure 2.7, adding new attributes and entities and using arrows to show the relationships between tables. If you're not sure where an attribute, such as author order, goes, don't worry. Get it listed. You'll go through more analysis attributes, entities, and relationships before you settle on a final form. The normalization guidelines. Basically, the normalization guidelines are a set of data design standards called normal forms. 5 normal forms are widely accepted, although many more have been proposed. Making your tables match these standards is called normalization. The normal forms progress in order from first through fifth. Each form implies that the requirements of the previous forms have been met. If you follow normalization rule number 1, your data will be in first normal form. If you follow normalization rule number 3, your data will be in third normal form, as well as in first and second normal form. Following the normalization guidelines usually means splitting tables into 2 or more tables with fewer columns, designing primary key and foreign key relationships into the new, smaller tables so that they can be reconnected with the join operation. One of the main advantages of splitting tables according to the normalization guidelines is the reduction of data redundancy within tables. This may seem confusing when the existence of matching primary key, foreign key hooks means that these columns are duplicated. But controlled duplication is not the same thing as redundancy. In fact, the maintenance of intentional duplication, that is, consistency between primary and foreign keys, is a major purpose of referential integrity. The normalization guidelines, like entity relationship modeling, were developed as part of the academic work on database theory. While they are extremely useful, they can be followed too slavishly. Most database designers find that putting their data in third or fourth normal form is usually as far as they need to go. First normal form. First normal form requires that each row and column intersection there must be one and only one value, and that value must be atomic. There can be no repeating groups in a table that satisfies first normal form. This design principle reveals a problem with the new sales table. How will you handle a single sales order that includes multiple books, as shown in figure 2.8? The general information is at the top of the sales order form. The order number, store number, and order date. Each numbered line contains details on a title. Lines used varies from order to order. Recording multiple book numbers in one title_ID column, as shown in figure 2.9, violates first normal form. Adding columns like Title 1 or Title 2 is just a disguise for repeating groups and leaves you with the same problems. It's not a great solution, practically speaking. As soon as a sales order includes a third book, you'll have to restructure the table again, adding a Title 3 column. Since all data must be represented in regular rectangular tables, multiple entries just don't fit the model. Where there are repeating columns, the current design involves a master table, sales, for the sales order as a whole, and a detail table, sales details, to hold information for individual order lines in the sales order. Figure 2.10. Notice that entity relationship principles would have led to the same conclusion, since this is a one-to-many structure. One sales order, many lines. While you're looking at repeating fields, also make a note to break up any compound columns into their elements. Address needs to have a separate columns for city and state, for example. Second normal form. The second normalization rule applies only in tables whose primary keys consist of multiple columns. It states that every non-key column must depend on the entire primary key. A table must not contain a non-key column that pertains to only part of a composite primary key. Putting a table into second normal form requires making sure that all the non-primary key columns, the columns that give information about the subject but do not uniquely define it, relate to the entire primary key and not just to one of its components. To illustrate, look at the contract column in the title authors table, figure 2.10. Does it apply to each author title combination? If each author on a book has a separate contract, it does. But if the company signs contracts only when all authors are in agreement, it doesn't. In this case, your company's legal division informs you that a contract is about a book, not about each individual author, and you move the column to the titles table, figure 2.11. This illustrates why database design is tricky. Your decisions often depend on the particular business model your company uses. To summarize, second normal form requires that no non-key column be a fact about a subset of the primary key. It applies when the primary key is made up of more than one column and is irrelevant when the primary key is one column only. Third normal form. Third normal form applies the principle addressed by second normal form in a more general way. It's not limited to composite primary keys. Third normal form requires that no non-key column depend on another non-key column. Each non-key column must be a fact about the primary key column. In the authors table, the primary key is AU_ID. When you check each column, you find that AU_ORD, the position of an author's name on a multi-author book, is not about an individual author, AU_ID, because an author might have several books and might occupy a different position on each, first, second, or third author. Author order really concerns each author-title relationship. The same is true of royalty per. Both of these columns belong in the title authors table. The quantity_ordered and quantity_shipped columns in the sales table also illustrate this principle. They concern individual line items, not the whole sales order, and should be moved to the sales details table. The date_shipped column is more of a puzzle. If orders are shipped only when all line items are ready, date_shipped applies to the order as a whole and should go in the sales table. If items are shipped as they become available, the column belongs in the sales details table. Since books are often out of print or otherwise unavailable, we'll assume the second model. The revised diagram is shown in figure 2.12. Analyzing the structures of these tables, you'll see that they satisfy both second and third normal forms. They satisfy second normal form because every non-key column is a fact about the entire primary key. They satisfy third normal form because no non-key column is a fact about another non-key column. To summarize, every non-key column must describe the key, the whole key, and nothing but the key. Fourth normal form. Fourth normal form forbids independent one-to-many relationships between primary key columns, and non-key columns. We'll use a rather unlikely example as an illustration. One author can have many cars and many pets, but there is no connection between cars and pets, even though each is legitimately related to a particular author. Putting these two different kinds of information in the same table can lead to unsightly blanks where there are more pets than cars, as in Green's case, or more cars than pets, as in Ringer's case. Deleting a car or a pet, if a car dies or a pet moves to another home, could also cause blanks in rows. The problem here is with the spurious relationship that seems to exist between cars and pets by virtue of their positional association in the row. It is better to put each of these entities in a separate table and to record their relationship in an author to an author by using the author ID as a foreign key column. For example, reviewing the database design. Let's review the process by which the design of the Book Biz database was developed. We started by proposing 4 tables: authors, titles, publishers, and editors. It seems intuitive to design a table for each of these things. The entity relationship approach states explicitly that each independent entity be represented by a base table. Entity relationship theory also called for 2 more base tables, one to model the association among titles and authors, title authors, and one for the association among titles and editors, title editors. We later added the sales and sales details tables. That leaves only one Book Biz table undescribed, the ROI schedule table, which lists the royalty rate to which authors are entitled as a function of the starting rate and the number of books sold. The ROI schedule table is a lookup table used primarily for reference purposes. Its data will not change unless the royalty schedule itself changes, which would happen only if an author's contract were renegotiated or a new title added. That makes 9 tables in all. Before we go into more detail about the full Book Biz database, take a look at the final data structure diagram, figure 2.13. Each box in the diagram represents a table with its name and the names of its columns inside it. The lines connecting the boxes represent relationships among the tables, showing the anticipated joins between them. Other joins are also possible. These are just the explicitly planned ones. The arrowhead on one end of the line between 2 tables indicates a many-to-one relationship between the tables. For example, there can be many titles to one publisher, but there can't be many publishers to one title, so the arrowhead is on the title's side. The n:1 notation near the line means the same thing: many titles, one publisher. Some diagrams use a multi-headed arrow on the many side of the line. Summarizing the Book Biz database. Let's take a closer look at the 9 tables in the Book Biz database to better familiarize you with the material on which the examples in the rest of the Practical SQL Handbook are based. There are more Book Biz details in Appendix D. The Book Biz database keeps track of the activities of 3 subsidiary publishing companies. Since the fiscal arrangements of the subsidiaries are not independent, the parent publisher has chosen to maintain a single database. The publisher's table contains information about the 3 publishing lines, their identification numbers, names, and addresses. For each author under contract with any of the publishers, the author's table contains an identification number, social security number, first and last name, and address information. The editor's table contains similar information about each editor, with the addition of a position column that describes the type of work the editor does, acquisitions or project management. For each book that has been or is about to be published, the titles table contains an identification number, name, type, publisher, identification number, price, advance, year-to-date sales, contract status, comments, and publication date. The numbers in the year-to-date _ sales column, which will change as more books are sold, might be kept current in one of several ways. By making periodic entries using the data modification commands, by coding logic into an application program that automatically updates year-to-date _ sales whenever a sale is entered into the sales details table, by using SQL to define a trigger that accomplishes the same automatic updating. See Chapter 10. The titles and authors are represented in separate tables that can be linked with a third table, the title authors table. For each book, title authors contains a row for every author involved, with information on the title ID, the author ID, the author cover credit order, which name comes first, and the royalty split among the authors of a book. The title editors table similarly links the titles and their editors. Instead of cover credit order, it lists editing order that it's possible to find who was the first or last editor. The ROI schedule table lists the unit sales ranges and the royalty connected with each range. The royalty is some percentage of the net receipts from sales. The percentage is used to calculate the amount due each author based on sales of his or her book. The sales table has top-level information about each purchase order received from bookstores. Sales order number, assigned by the publisher, store identification, purchase order number, assigned by the store, and date. The sales details table contains information about each line in the purchase order, assuming any purchase order may involve more than one book. Title, quantity ordered, quantity shipped, and date shipped. Of course, a real publisher's database would be much more complex, with tables for stores, employees, distributors, production costs, vendors, subcontractors, and the like. As an exercise, you might try sketching some of these tables and deciding how they would relate to the tables already in Book Biz. However, these 9 tables do represent enough material to work with for learning SQL, and they are used throughout this book. Testing your database design. Once you've come up with a proposed design for your database, you should create the tables and insert some data. The next chapter gives detailed information on these procedures. Then you should test your design by running queries and updating the data. Your tests may reveal oversights in the design. Database designs are seldom satisfactory when based entirely on theory. It's essential to play with your design interactively before undertaking serious production efforts, especially if you plan to use it in an application that will involve thousands of lines of programming code and tens of thousands of rows of data. Don't wait until you've invested hundreds of hours in a flawed design. You can avoid problems by working interactively with a prototype of the database. Other database definition considerations. If you were about to put a real-world database online, you'd have several additional critical issues to consider before proceeding: indexing, security, and integrity. Deciding which columns to index and what kind of index is best for each column is an important part of database implementation. It is covered in Chapter 3. Security is discussed in Chapter 10. Planning for data integrity is a major part of database design. It involves setting up a system to make sure changes to one piece of data apply to all copies of that data anywhere in the database, so that you won't end up with orphans or inaccuracies. An example using BookBiz might be discovering that an author's ID number was incorrect. If you changed it only in the author's table, you'd never again be able to find out what books that author had written, because that author's ID number in title authors would no longer match the ID number in authors. In order to access the information in title authors, you'd have to make sure that when the author ID changed in authors, it also changed in title authors. Summary. This chapter walks you through the steps of database design using the sample database BookBiz. You start off looking at some basic considerations for database design, including characteristics of good and bad design. Next, you look at how you define attributes and entities and what their relationships to each other mean. To make sure every column is in the right table, you check columns and tables closely against the normalization rules. Finally, you look at the database as a whole. Does it work? Can you get the reports you need? Once the database design is in place, you can create the database and its tables and add data. Chapter 3 covers the SQL, DDL, and DML commands for creating objects and adding data.